Okay, this question is very similar to the last question. The only difference in this case is that we have forces or a collection of forces and moments in all four quadrants of our coordinate system. So again, we want to replace this system with, in the first instance, a single force and a moment applied at the origin, and then a single force positioned along the y-axis this time rather than the x-axis. So the solution procedure is going to be the exact same as before. We are going to say that the sum of the forces in the x direction for system A must equal the force in the x direction in my equivalent system B. Okay, so we simply evaluate the horizontal component of all forces in our system A. So what have we got? Fxb is equal to 18.58 newtons. Excellent. And then we can do the exact same thing for the forces in the vertical direction. Fyb equal to 185.44 newtons. Okay, excellent. Now, these are again the orthogonal force components of the equivalent resultant force. So I essentially again will use the geometry of a right angle triangle to determine the magnitude and orientation of the resultant force in system B. So let's sketch it out. So we have a force. This force will be applied at the origin. So we draw on our coordinate system. We have an origin O. Now the horizontal component Fxb was 18.58. So positive indicates it goes to the right. And the vertical component was 185.44. Again, positive indicating upwards. You're only sketching, so we don't need to worry about the scale of these lines. They're clearly not to scale. So 185.44, and the horizontal component was 18.58. Well, that means the resultant force looks like this. Closing out the right angle triangle, we're going to label this or B, the magnitude of the resultant force in system B, and it's orientated at an angle theta B with respect to the horizontal axis. So again, simply utilizing the geometry of a right angle triangle, we can say that and this is anti-clockwise from the positive x-axis. Okay. All right then, so that's half the battle. The remaining thing is to work out what's the equivalent moment. Okay, so we've established force equilibrium. Now we need to get the equivalent moment. So once again, let's state the facts. The sum of the moments in system A must equal the equivalent moment in system B. So we're going to simply take moments about the origin. So evaluating that, we have MB is equal to 371.59 Newton meters. All right, and so we can sketch out our system. So we can replace everything in system A. Did we call it system A? We call it system B this time. So our starting system is system B. Right, we can take everything in system B and replace it by a force applied at the origin with a magnitude of 186.37 newtons, orientated at an angle of 84.3 degrees counterclockwise from the positive x-axis. But we also have to apply a moment clockwise about the origin. Let's just label that, or B equal to, and then this can be MB. The moment we apply is equal to 371.59 Newton meters. Okay, excellent. This is what we are going to call system C. If we started off with system B, this can be system C. Okay, excellent. Now we're going to follow the same line of attack as we did in the previous question, and we are now going to take system C and replace it with a system in which there's no directly applied moment. We only have a force applied, but our force no longer needs to be applied at the origin. In fact, we can apply it anywhere along the y-axis. So our task is to determine, how do I generate a moment, a clockwise moment of 371.59 Newton meters by shifting the applied or the resultant force RB along the y-axis. And I have to determine the distance along which I shift it up the y-axis. So again, if you followed the previous example, there should be no surprises here. We're just simply going to take the moment that I need to generate, which is 371.59 Newton meters, okay? That's equal to a force times a lever arm. The relevant force in this case is going to be the horizontal component of RB, which is going to be 18.58, and that's going to get multiplied by a lever arm dy, essentially the distance along the y-axis the force is shifted. Okay, and we can simply say, therefore, solving dy is going to equal 20 meters. Okay. All right then, so let's sketch out the system. RB equal to 186.37 newtons. That force has a horizontal component of 18.58, and it's that horizontal component that is acting at a lever arm distance of, 20 meters, that is generating the moment, so I no longer need to directly apply a moment to the origin. Okay, so, and it's also worth pointing out that the vertical component of that force, which was 185.44, that is applied, or that's the line of action of that force passes through the origin, and it therefore has no moment effect. Okay, so that is essentially what we're going to call system D, which concludes this particular question.